Hi, today we're going to talk about working with probabilities and specifically solving problems that have probabilities in them. It's really important to keep in mind if you're told that events are independent or disjoint, we learned about those last week, that's really important information to have. If events are independent, it means the outcome of one does not affect the other. And so we're talking about things that have no relationship with each other. So if we're talking about one coin flip and a second coin flip, it doesn't matter what happens on the first one for how the second one's going to go, right? The coin doesn't care. So things like rolling die, pulling cards out of a deck if we're replacing the card back in, flipping coin, those are all independent events. A lot of things in the real world are not independent. There's some relationship between the different things we're looking at. And so if we're not told they're independent, we have to go forward with the assumption that they are related to each other. They are dependent, okay? Same thing with disjoint. If we're told that they're mutually exclusive, that we can't have overlap between the outcomes, well, then that's important information. It means we could use the simple addition rule. The chance of A or B happening is just the probability of A plus the probability of B if they're disjoint events. But in the real world, that's usually not true. Usually we can have both A and B happen sometimes. There's some overlap. So for most problems we're solving with probability, unless you're told they're independent or disjoint, this is the way I want you to treat them. I want you to write down what you know, and specifically, if you're told information about two different things, I want you to write it down in a table. So here's some information. Let's say you're told that in a town, 10% of the people have COVID-19. So there's one piece of information about one variable, one thing we care about, prevalence of COVID-19. Let's say you're also told that 3% of the population in the town has to be hospitalized. Okay, so there's a second piece of information about a second outcome, right? Being hospitalized. Now, the third piece of information you're given is that of the people with COVID-19, 20% of them have to be hospitalized for the disease. Okay, so we're given three pieces of information. We know 10% of people in the town have COVID-19. Of those, 20% have to go to the hospital. We also know that 3% of the population of the town in general has to go to the hospital. So those are three pieces of information. We're going to write that down in a contingency table. So what I'm going to do is I'm going to write down across the top one of the variables. I'll write COVID-19 or not COVID-19. So that's going to be the columns of my table. I'm going to have rows going down that say hospitalized or not hospitalized. So I've got my two variables, COVID-19 or not, hospitalized or not, and I am going to put totals at the bottom. This is now a contingency table. So we've got two variables and we're going to look at the relationship between the two. Now we need to write in what we know. We know a couple marginal probabilities. We know that 10% of the population has COVID-19. So that's actually down here at the bottom. I'm going to write 0.1. 10% have COVID-19. We know 3% of the population is hospitalized, so that's a marginal probability that goes over here, 0.03. And then we know one other piece of information. We know that 20% of the people with COVID-19 are hospitalized. So if we think about that, we know that 10% of people have COVID-19. Of those people, so this is a conditional probability, we're looking just within those people. Of those people, 20% are hospitalized. That means this number is going to be 20% of that. So 0.02, 2% total are people who are hospitalized with COVID-19. Now see, these aren't disjoint events. We can have both happening at the same time. They're also not independent events. Whether you have COVID-19 or not has a relationship with how likely you are to be hospitalized or not. That's why it's so important to put this in the table and not just try to use our simple multiplication or addition rules to answer questions about these things. Now, so what we need to do is fill out the rest of this table. And once we have that, we could answer all kinds of questions really quickly with it. So one other thing about these tables, in the lower right corner, the grand total is always going to be 1. The probability of someone being within this population is 1 for people that we're looking at. Now, to fill in the table, we need to basically make all of the rows and columns add up to each other. So up here, we know that 3% of people are hospitalized, 2% of them are COVID-19 patients. That means 1%, 0.01, must be these non-COVID-19 but hospitalized people. We have 0.02, we need to get to 0.03, so it must be 0.01. We're taking the total, subtracting the amount we have here to get the amount there. Same thing here. So we know that 2% of people are COVID-19 and hospitalized. We know a total of 10% of people are COVID-19. That means 0.08 are the not hospitalized COVID-19 patients. Now, we put that 1 in the lower right corner. That's so important because that allows us to add up here in the margins as well. We know 3% of people are hospitalized. That means 97% are not hospitalized, right? And over here we have 10% with COVID-19. That means 90% do not have COVID-19. So now we've almost filled in our table. There's just one more gap here, and we can get to it by subtracting the non-COVID-19 hospitalized from non-COVID-19 in general, or we can do it by going across on this row. Either way, it should give us the same number, and that's actually a really good way to check that you haven't made any arithmetic errors as you fill in the table. So the easiest way for me to do this is we need to get to 90%. We're at 1%, we need to add 89. And as a check, 89 plus 8 gives us 97, so it looks like we're good. So we now have a full table that tells us about the relationship between having COVID-19 and being hospitalized in this little town. And I could ask a whole bunch of questions that you could answer really quickly. I could say, what is the probability that someone in this town does not have COVID-19 and is not hospitalized? And we just look at, okay, not hospitalized, not COVID-19. We say 89%, 0.89. What's the probability that someone has COVID-19 but is not hospitalized? Well, COVID-19, not hospitalized, 8%. So notice those are joint probabilities. I'm asking about two things happening at once, right? And so I could ask it, what's the probability someone does not have COVID-19 but is hospitalized? Well, not COVID-19, hospitalized, that's 1%. So we just answered 3 questions really quickly, right? We could also answer questions about these marginal probabilities. What's the probability someone does not have COVID-19 in this town? We look down here, 90%. What's the probability someone is in the hospital? 3%. So a contingency table like this is a good way to try to answer questions that involve probabilities when we are told they are not independent or disjoint. If we just use the simple multiplication or addition rules, we will get them wrong. This is the way to get them right. Make a table like this, put in the information you know. If you're given 3 pieces of information, you can fill in the rest quite quickly. And then you can work through all of those questions you're asked about in a pretty quick manner.